Good morning, students. Today we are going to the last part of solid state chemistry, that is electrical properties in solids. Electrical properties in solids. Based on the electrical properties, material or substances can divide into three types. One is conductor, and second one is insulator, and the third one is semiconductor. Then conductors. What are conductors? Conductors are the material or substances which conduct the electricity at maximum extent. Conductors are the material or substances which conduct electricity at maximum extent. Examples: metals, copper, then aluminium, iron, etc. Insulators. Insulators are the type of substances or material which do not conduct electricity. It's a material or substances which do not conduct electricity is called, the type of material is called insulator. Examples: rubber, plastics, then wood, etc. These are the material which do not conduct electricity. Then the third one is semiconductor. Conductors are the material or substances which conduct electricity at smaller extent. In conductors, larger extent conduct electricity, but in semiconductor, these are they conduct electricity at smaller extent. Examples: germanium, silicon. Germanium and silicon. Then these electrical properties can also be studied by band theory. Electrical properties can also explain with the help of band theory. Band theory. In first PUC, you are already studied molecular theory of orbital, molecular orbital theory. In that, lower energy is called as bonding orbitals. Two atomic orbitals are combined to form molecular orbital. That lower energy orbital is called bonding molecular orbital, and higher energy molecular orbital is called as anti-bonding molecular orbital. So here also lower energy orbitals are called as valence band. Higher energy is called as conduction band. Lower energy is called as valence bond, or in short form VB. It is conduction band. See. So let us see one by one. In case of conductors, valence band, it is partially filled or completely filled. This valence band is partially filled or completely filled, and the conduction band and valence band overlap with each other. Conduction band not bond, it is band. Conduction band and valence band are overlap with each other. If we heat or increase the temperature, electrons at the valence bond jump to the higher energy state, that is conduction band. Electrons are jumped to the conduction band and it conducts electricity. In this, valence band are partially filled or completely filled, and conduction band and valence band are overlap with each other, and if we increase the temperature, electrons present in the valence band jump into the conduction band and conducts electricity. This is the theory in case of conductors. So, in case of insulators, here the conduction valence band and the conduction band. This is valence band and conduction band. Valence band and conduction band. The gap between the valence band and conduction band is large. So, the definition itself shows that it do not conduct electricity. So, the gap between the valence band and the conduction band is large, and this gap is also called as forbidden gap. This gap between the conduction band and valence band and conduction band is large. So, electron cannot jump from valence band to conduction band, and electrons are fully filled. But if we increase the temperature, electrons cannot jump to the conduction band because the gap between these two is very large compared to other types. So, it do not conduct electricity. Then, third one is semiconductor. Semiconductors. Semiconductors are the conductors which conduct electricity at smaller extent, isn't it? So, the electrons are filled in the valence band and conduction band is empty. The gap between the conduction band and valence band is small. Here the gap between, in case of insulator, the gap between the valence band and conduction band is large. In case of semiconductors, it is small. So what happens if we increase the temperature or heat the substances? The electron present in the valence band, it jumps to the, or it goes to the, jump to the higher energy state, that is conduction band. So obviously it conducts electricity, but the gap is small. But in case of conductors, it is overlap. So here no gap. So it conducts electricity at maximum extent, but here gap is small, and if we heat the substance or increase the temperature, electron present in the valence band is jumped to the conduction band higher energy state, and it conducts electricity at smaller extent. This is about the band theory of the solid. Now let us discuss about the types of semiconductors. First one is intrinsic semiconductor and second type is extrinsic semiconductor. Intrinsic semiconductor means it is a pure semiconductors. If for example silicon or germanium is a type of intrinsic semiconductor, if they consider a silicon crystal, in this silicon is a group 14 element. Silicon contains 4 valence electron in the outermost shell So these electrons are combined to the neighboring silicon atom to form a covalent bond, and these electrons shifted to the neighboring atom delocalized itself into the neighboring atom and conduct electricity. When the temperature rise or heating given means that semiconductor conducts electricity. So if we add any impurity atom, that may be group 13 element or group 15 element, if we add impurity atom to the pure semiconductor, that process is called doping. Adding of impurity to the pure semiconductor to increase the conductivity, to increase the electrical conductivity, that process is called doping. Doping. Now, the second type, intrinsic semiconductor. In that, first type is P-type semiconductor. P means positive type extrinsic semiconductor. This is a pure intrinsic semiconductor. If I consider group 13 elements, that is boron, aluminium, gallium, indium and thallium. If I replace this silicon atom with aluminium atom, that means we have to introduce impurity to the pure intrinsic semiconductor. Aluminium contains, these group are trivalent. That means in the outermost electron shell, electron is 3 only. Aluminium contains 3 electrons. So those 3 electron is shared with the other neighboring silicon atom and form covalent bond. But one more electron is not there. So here create a hole. Here one electron is there, isn't it? 3 electrons of aluminium combine to form covalent bond with the neighboring silicon atom. But to combine the 4th bond, here electron not there. So here create a hole. This contains positive charge. In P-type semiconductor, holes are the charge carrier. How it is charge carrier? Because if I consider the neighboring silicon aluminium bond, this will shift here and create here one hole. Like this happened here. This will shift here. Here create hole. So holes are alternative neighboring groups are holes created here. Holes and single electron. Holes are the majority carrier. Charge carrier is holes. Remember that one. For that purpose, here conduct electricity. This type of semiconductor is called P-type semiconductor. Then N-type semiconductor. N-type semiconductor. N represents small letter. N represents negative charge. If I consider silicon crystal, if suppose pentavalent or pentavalent group of atom introduced into the pure semiconductor, intrinsic semiconductor, pentavalent means group 15, nitrogen, phosphorus, arsenic, month. If suppose I introduce phosphorus. Phosphorus means it's a pentavalent. Outermost shell contains 5 electrons. 1 electron, 2, 3, 4, and 1 more electron here. These 4 electrons shared with the silicon electron and combined to form covalent bond, and 1 more electron present here, isn't it? So this electron is the reason, and this is move entire crystal. This electron is move entire crystal and rise the electrical conductivity. For this purpose, the delocalization of this electron to the entire crystal, as a result, electrical conductivity increases. This type of semiconductor is called N-type semiconductor. Here, electrons are the charge carrier. In B-type, holes are the charge carrier. In N-type semiconductor, electrons are the charge carrier. Sometimes in annual exams, differentiate between the N-type and P-type, P-type and N-type semiconductor question may come for 2 marks, 3 marks. So you have to write the difference between the P-type and N-type semiconductor. This is about the electrical properties in solids. Now let us study about the last topic of this chapter, that is magnetic properties in solids. See, almost all the substances around us, they show some kind of magnetic properties, isn't it? Either it may be attracted by the magnet or repelled by the magnet, or in some cases some substances show strong attraction towards the magnet. What is the reason for this one? Reason is the presence of electron. You know that the substances are made up of large number of atoms. Atoms consist of nucleus, isn't it? And electrons revolving around the nucleus in a circular path. Electrons are revolving around the nucleus. This electron showing 2 types of motion. One is orbital motion. The second one is spin motion. What is this orbital motion? Orbital motion, electrons revolving around the nucleus in a orbit. That type of motion is called orbital motion. And spin motion means electron along with the orbital motion, electron revolving around its own axis. Bhumi Suryana sutta suttuvudanna electron ಗೆ ಕಂಪೇರ್ ಮಾಡಿದ್ರೆ it is orbital motion. Bhumi tanna sutta suttudu. That means electron revolving around its own axis. That is spin motion. Due to these 2 motion, magnetic properties are observed. So, based on the substances, based on the magnetic behavior, substances are classified into total 5 types. One is paramagnetic substances, second one is diamagnetic substances, third one ferromagnetic substances, ferrimagnetic substances and anti-ferromagnetic substances. Let us see one by one with examples. So the first type is paramagnetic substances. Paramagnetic substances are the substances which are weakly attracted towards the magnetic fields. Which are weakly attracted towards the magnetic field. The paramagnetic substances in that magnetic behavior observed due to the presence of one or more unpaired electron present in the substances. Presence of one or more unpaired electron present in the substances. So example is copper sulfate, manganese sulfate and liquid O2. I already told the presence of unpaired electron is required. So in the substance, where is unpaired electron? So I considered copper sulfate as an example. In copper sulfate, copper is in +2 oxidation state. Copper atomic number, you know that it is 29. If I wrote the outer electronic configuration, that is 3d10 4s1. So copper oxidation state is +2. So I have to remove the 2 electrons from the outermost shell, that is 4s from this 1 electron, and 3d10 I have to remove 1 electron. So that is 3d9 I got. So if I arrange the electrons in the 5th shell, one unpaired electron is present, isn't it? So unpaired electron is there means this copper sulfate shows paramagnetic behavior, and the strength of the magnetic field or magnetic behavior, that is magnetic moment, we can calculate it by the equation nu is equal to square root of n into n plus 2, where n is the number of unpaired electron present in the substances, where n is the number of unpaired electron present in the substance. This is about the paramagnetic substances. So the second type is diamagnetic substances. Diamagnetic substances are the substances which do not attract with the magnetic field, or no attraction towards the magnetic field. And the diamagnetics, one more definition is diamagnetic substances are the substances which have repelled by the magnetic field. Examples: water, benzene, NaCl, etc. Here, for the repulsion or repelled by the magnetic field, the reason is here the substance having all the electrons are paired. That means no unpaired electrons are present in diamagnetic substances. The next one is ferromagnetic substances. Examples: iron, nickel, cobalt, etc. Ferromagnetic substances are the substances which are strongly attracted by the magnetic fields, or in other words, it is a permanent magnet. These substances are permanent magnet, and these are strongly attracted by the magnetic field. If I consider a iron substance, these are the iron atom arranged in a substances. If I consider iron is a electropositive, all the metals are electropositive, that means they release electron and give charged species, right? If iron give Fe3 plus electron, right? So this charged group of charge, that means positive charge in one side and electron is negative, right? So both are there in iron. So these are grouped together before applying the magnetic field. This is a group of charge, positive and negative charge. This is called domain. We call it as domain. These are arranged in parallel direction when the magnetic field is applied. Before applying the magnetic field, these domains are arranged in random way. Order of arrangement is random before applying magnetic field. After applying the under magnetic field, these are arranged in a parallel direction and gives a strong attraction towards the magnetic field. So the fourth one is anti-ferromagnetic substances. Anti-ferromagnetic substances are similar to ferromagnetic substances, but the only difference is here domain structure is similar to ferromagnetic substances. Domain in this ferromagnetic substances, domains we saw that positive in means same orientation. Orientation of the domains are in the same direction, but domains here oppositely oriented. You see here one direction, this one, here negative is there, but this one opposite to this one. So this one and these two cancel each other, isn't it? So the net magnetic moment, that is nu, is equal to 0. Why 0? Here it is cancelled to each other. This is one direction, means this is opposite direction. So this is one direction and the second, third, fourth one is opposite direction. So cancel to each other. The total substances, that magnetic moment, magnetic strength is here 0. But ferromagnetic is opposite to anti-ferromagnetic. Why? Their strength is more. The only difference is the orientation of the domain is opposite compared to the ferromagnetic substances. This is about the anti-ferromagnetic substances, and the example is MnO, MnO2 and M2, Mn2O. These are the examples. So the last one is ferromagnetic substances. Ferromagnetic substances, here the domains are arranged parallel and anti-parallel, parallel and anti-parallel with unequal numbers. With unequal numbers. In anti-ferromagnetic we saw that one is parallel, means one more is anti-parallel, right? That is in same number. But in ferromagnetic substances, the domains of the substances are arranged parallel and anti-parallel in unequal numbers. That means this is parallel, means see, these two direction is like this, plus minus, but these two orientation is opposite direction, isn't it? So in unequal number, isn't it? Like this arrangement, like this type of arrangement or substance is called ferromagnetic substances. If we heat these type of substances, it loses its magnetic field and become paramagnetic substances. And compared to the ferromagnetic substances are less attracted by the magnetic field. One more point is, ferromagnetic substances are less attracted compared to the ferromagnetic substances. And examples is Fe3O4, that is magnetite, and ferrite like MgFe2O4. This is the main examples. Fe3O4 magnetite you know, and you will study in upcoming chapters. This is about the ferromagnetic substances. First chapter is over. Notes will give through WhatsApp, and read well, study well, and prepare for the unit test. Enjoy the online classes. Thank you.